So we're given a series here, and they say, what series should we use in the limit comparison test? Let me underline that, the limit comparison test, in order to determine whether S converges. So let's just remind ourselves about the limit comparison test. If we say that we have two series, and I'll just use this notation, A sub n, and then another series, B sub n, and we know that A sub n and B sub n are greater than or equal to 0 for all n, if we know this, then if the limit as n approaches infinity of A sub n over B sub n is equal to some positive constant, so 0 is less than that constant is less than infinity, then either both converge, both converge, or both diverge. And it really makes a lot of sense because it's saying, look, as we get into our really large values of n, as we go really far out there in terms of the terms, if our behavior starts to look the same, then it makes sense that both these series would converge or diverge. And we have an introductory video. On this in another video. So let's think about what if we say that this is our A sub n. If we say that this is A sub n right over here, what is a series that we can really compare to that seems to have the same behavior as n gets really large? Well, this one seems to get unbounded. This one doesn't look that similar. It has a 3 to the n minus 1 in the denominator, but the numerator doesn't behave the same. This one over here is interesting because we could write this. This is the same thing as the sum n equals 1 to infinity. We could write this as 2 to the n over 3 to the n. And these are very similar. The only difference between this and this is that in the denominator here, or in the denominator up here, we have a minus 1, and down here we don't have that minus 1. And so it makes sense, given that that's just a constant, that as n gets very large, that these might behave the same. So let's try it out. Let's find the limit. And we also know that the A sub n's and the B sub n's, if we say that this right over here is B sub n, if we say that's B sub n, that this is going to be positive, or this is going to be greater than or equal to 0 for n equals 1, 2, 3. So for any values, this is going to be greater than or equal to 0. And the same thing right over here. It's going to be greater than or equal to 0 for all the n's that we care about. So we meet these first constraints. And so let's find the limit as n approaches infinity of A sub n, which is, I'll write in that red color, which is 2 to the nth power over 3 to the n minus 1 over B sub n over 2 to the nth over 3 to the nth. So let me actually do a little algebraic manipulation right over here. This is going to be the same thing as 2 to the nth over 3 to the n minus 1 times 3 to the n over 2 to the n. Divide the numerator and denominators by 2 to the n. Those cancel out. And so this will give us 3 to the n over 3 to the n minus 1. We can divide the numerator and denominator by 3 to the n, and that'll give us 1 over 1 minus 1 over 3 to the n. So we could say this is the same thing as the limit as n approaches infinity of 1 over 1 minus 1 over 3 to the n. Well, what's this going to be equal to? Well, as n approaches infinity, this thing, 1 over 3 to the n, that's going to go to 0. So this whole thing is just going to approach 1. And 1 is clearly between 0 and infinity. So the destinies of these two series are tied. They either both converge or they both diverge. And so this is a good one to use the limit comparison test with. And so let's think about it. Do they either both converge or do they both diverge? Well, this is a geometric series. Our common ratio here is less than 1. So this is going to converge. This is going to converge. And because this one converges by the limit comparison test, our original series S converges. And we are done.